Okay, a very good evening to all the attendees and to our guests, Professor Ewine and Professor Andrew Fabian, who have joined us today for delivering their special public lectures. And these special public lectures are in the last of the series of the special public lectures which the National Academy of Sciences India Delhi chapter and the MHRD-Institution Innovation Council, Deen Dayal Upadhyaya College University of Delhi have been organizing for last 3 months. And they have been organized under the aegis of the DBT Star College program. And I would like to acknowledge Professor Joy Ghatak, who is the chairperson of the NASI Delhi chapter, who will be joining us very shortly in the smooth organization, planning, conceptualizing these lectures. So before I formally introduce Professor Ewine, I would like to request my co-panelist, Professor G.C. Anupma, who is a senior professor at Indian Institute of Astrophysics and also the president of the Astronomical Society of India, to kindly brief the two experts and the attendees about the research, about the work which is going out at the Indian Institute of Astrophysics, as well as the activities which are there at the Astronomical Society of India. Yeah.
Thank you, Manoj. Good evening to everybody. As Manoj mentioned, I'm a senior professor at the Indian Institute of Astrophysics and also the president of the Astronomical Society of India. The Indian Institute of Astrophysics is probably the oldest institute in the country, and particularly in astronomy. We trace our origin to Madras Observatory, which was started by the East India Company in 1786. And this was actually started in Madras, or Chennai as it is now called. And we moved to Kodaikanal when a solar observatory was set up there. And this was sometime in 1800s, in the late 1800s. And as the Indian Institute of Astrophysics, we were formed in 1971 as an autonomous institution, totally funded by the government of India. And so we are now celebrating our 50th year as the Indian Institute of Astrophysics. I has several observatories. We still operate the Kodaikanal Solar Observatory, which is the oldest one that we have. And in the late 1960s, we set up the Vainu Observatory, where we have optical telescopes, the largest being the 2.3 meter Vainu telescope, which was commissioned in 1986. And this telescope was completely built in India. In the late 90s and early 2000, we established a high altitude observatory in Ladakh, in a place called Hanle. It's at an altitude of 4,500 meters. Currently, we have a 2 meter telescope there and a 0.7 meter wide field robotic telescope, which is primarily used for observations of transients. The 2 meter telescope, which is called the Himalayan Chandra telescope, is the most productive telescope in the country today in the optical, as far as optical telescopes are concerned. And the Hanle Observatory, or the Indian Astronomical Observatory as it is named, also has other facilities there, particularly for the observations of TV gamma ray observations using the atmospheric Cherenkov technique. There is an array called the Hager. It's a gamma ray array telescope, and another one which is coming up. This is an imaging Cherenkov telescope called the MACE, or the Major Atmospheric Cherenkov Experiment. It's a 21 meter dish and very similar to the MAGIC telescopes. We have proposed to set up a 2 meter class solar telescope in the Ladakh region, not at Hanle, but on the banks of the Pangong Lake in a place called Merak. The land has been acquired, and we are waiting for the necessary funding, the approvals and funding for beginning the construction of the telescope. India is also participating in the 30-meter telescope. We are one of the partners of the 30-meter telescope. And the Indian Institute of Astrophysics is the nodal institute in the country for all the India TMT activities. So as a part of our participation in the 30-meter telescope, we will be providing several components, particularly connected with the primary segments control systems, the segment support assemblies, the actuators, and the edge sensors. And also part of the segments will be polished and delivered from India. We're also contributing to the telescope control in the observatory software. Now, coming to the society itself, the Astronomical Society of India was founded in 1972. It's the professional, it's a society for professional astronomers. And we also have, as associate members, people who are interested in astronomy and astrophysics. The society is particularly for the promotion of astronomy and related branches of science in the country. We hold science meetings, and there are several awards which are instituted by the society. In addition to our regular activities of holding lectures and scientific meetings, we also have a very active public outreach and education program. We have a subcommittee for public outreach and education, and this is a very active group of professional and amateur astronomers, a combination of both. And also, I wouldn't be wrong in saying that the Astronomical Society of India is probably one of the first professional societies in Asia to have a working group for gender equity. Now, this is another very active group, and we are trying to find ways and means of ensuring that the women who come into astronomy, we have a lot of young students doing research, but finally when it comes to people actually in the faculty, the number of women in the faculty is drastically reduced as compared to the number of students for various reasons. There is this two-body problem and various other reasons. So as a society, we are very conscious about this, and we are trying to address this problem as best as we can. So this is to give you a very brief introduction to the institute I come from and to the Astronomical Society of India. Thank you.
Thank you very much, Professor Anupma, for enlightening us about the activities which have been taking place at the Indian Institute of Astrophysics as well as at the Astronomical Society of India itself. So I requested Professor Dishoeck for giving a technical talk on, and she kindly agreed for it, and that is related to building stars, planets, and the ingredients for life in space. And for those who are not aware about her credentials, let me just introduce Professor Ewine, who doesn't need any introduction, but still as a customary, I have to introduce her. So she's the president of International Astronomical Union, and she's a professor of molecular astrophysics at Leiden University in Netherlands. She graduated at the Leiden in 1984 and held positions at Harvard, Princeton, and Caltech before returning to Leiden itself in 1990. The work of her group innovatively combines the world of chemistry with that of physics and astronomy to study the molecular trail from star-forming clouds to planet-forming disks. She has mentored several dozens of students and postdocs and has been heavily involved in planning new observational facilities such as the Herschel Space Laboratory, ALMA, and JWST. She has received many, many awards, including the 2015 Albert Einstein World Award of Science and the 2018 Kavli Prize for Astrophysics. She is a member of the Foreign Associate of several academies. As of 2018, she serves as the president of the International Astronomical Union. And she kindly agreed for delivering this talk when I highlighted that in India, we are celebrating the National Science Day that takes place on 28th of February. but all throughout the year, the theme has been a woman in science. So I request her to kindly share her screen and deliver the talk.
Hey, Manoj, thank you very much. Thank for this kind introduction. It's a real pleasure for me to be here virtually with you from my tiny little country, the Netherlands, in Europe. Very wet, actually, here at the moment. I'm really pleased to be here and to tell you a little bit about the story of how we build stars and planets in space, and also the possibilities for life elsewhere. But first, I want to make sure that, and to say that I hope that everybody who is online, and I really appreciate so many people being here online, that you're doing well. I realize that India has also been hit and suffering substantially from the corona pandemic. And I know that this had an impact on all of your lives. And I'm especially feeling also for the students who have had such a hard time now in getting lectures just online rather than being face-to-face at the universities. It does make a difference. Nevertheless, this pandemic has also opened up new possibilities, because it means that I actually can be with you virtually from Holland, rather than having to travel all the way to India. My last visit there was actually in 2017 in Pune, which I enjoyed very much. But now I'm able to give the lecture actually remotely. So that is certainly one of the gains that we've had in this pandemic. So what I hope to do with you here today is take you on a tour of the space between the stars, these clouds that you see over here, and to see how we actually build molecules in there, some chemistry that may or may not lead to the building blocks for life, as you see here, but also how we build planets like Jupiter or planets like Earth actually in these very tiny clouds. Before going into the astronomy part, one of my hobbies is actually looking at astronomy and art. And then you see that this question of the origin of stars and planets and where does our solar system come from, it's something that is not just limited to astronomy or scientists. It's something that has fascinated mankind throughout the ages. And here you see just a few of some of my favorite paintings here of the Dutch painter, Vincent van Gogh, the Starry Night that you see here with the Big Dipper over the Seine. But also, if you go to a completely different part of the world, Australia Aboriginals, they have the beautiful southern sky above them, very clear in the deserts. And there they have sort of their Milky Way dreamings, which are part of their cosmology. Other part of the world, in the Pacific Northwest, Canada, here you see the story of first raven that is actually stealing the sun from a dark box and putting it on the sky. And in more modern paintings, you have here one of my favorite stars by Kandinsky. But also in your country, in India, there are many examples of astronomy and art, and here I have just one of them representing here the stars of sciences. Okay, so origin of our solar system, where do we come from? Just to remind you that for those of you who are not experts in this field, that here we have our solar system, which of course has here our star, the sun, and then here the various planets. And one of the questions that we are going to look at is how unique is our solar systems. We have a number of small planets, terrestrial planets like Earth, and we have a number of gas giants like Jupiter. And how were they formed? And what led to this particular configuration? Now, our story actually starts in the very dusty clouds along the Milky Way that you see so beautifully here in this picture. And if you would look at the Milky Way from above, this is here a combination of astrophysical data with an artist impression, then the Milky Way would look as follows. Here we have the center of our galaxy. We now know this contains a black hole. In fact, the Nobel Prize for Physics was just awarded earlier this week to 3 scientists who discovered, actually worked on black holes and discovered the presence of a massive object here at the center of our galaxy. But our galaxy is a collection of some 200 billions of stars, and our sun is just one of those stars. And you see it's rather in the outskirts there. So we actually live on a small planet that is circling a rather ordinary star that is located somewhere in the outskirts of our galaxy. And then our galaxy is just one of several hundred billions of galaxies in the universe. So that makes the whole question of, are we unique, already puts that in a different light. Now, exoplanets were predicted or speculated about already centuries ago. You can go down to some of the writings of the ancient Greeks. But the scientific evidence for planets around other stars than our sun did not come until 2019. And in fact, that was awarded the Nobel Prize in Physics in 2019. And as I mentioned already, 2020, the black hole in the center of the Milky Way. So astronomy certainly has had its recent very important discovery. Now, this discovery of planets around other stars, these so-called exoplanets, has made several age-old questions brought them again to the forefront, such as how and where are the stars and planets born? How unique is our solar system? And which of these planets could be habitable? It's good to also look a little bit at how these planets are actually discovered. You can either discover them by the fact that they make a little pool, the planets on the mother star, and that you can see these tiny motions. But the easiest way to, and through which the bulk of the exoplanets are now being discovered, is actually through the so-called transit methods, where the planet goes in front of the star and it dims the light actually by a very tiny amount, usually much less than a promille of the light of the star. And through this method, and especially the Kepler satellite data, astronomers now know that on average, probably every star has at least one planet, but they are often of a size and a radius that is somewhere in between the planets that we know in our own solar system. So some of them are like Jupiter, some of them are even more massive than Jupiter, some of them may be Earth-like, but the bulk of them appear to be in this regime of the so-called super-Earths and mini Neptunes. Neptune is about 10 times the mass of the Earth, so somewhere in between Earth and Neptune, that's where the bulk of the exoplanets that have been found so far in terms of statistics that they have been, that they seem to be. So once they have been detected, then of course the next question is, what is their composition? What are their building blocks? How were they formed? Could they be habitable? And so these are the questions that I'm going to address in the next 40 minutes. And then especially as to how they were built. And directly related to that is coming back to our own solar system. How were we formed some 4.5 billion years ago? And again, there's been very exciting new results, most notably from the Rosetta mission, ESA mission, the European Space Agency, that actually landed on the surface of a comet for the first time in 2014. And sniffed the gases that came out of that comet. And so we'll talk about that at the very end. And that tells us something about the cold objects that are in the outer parts of our solar system. In the inner part of our solar system, we get information from these asteroids, like you see over here. And again, there have been just exciting missions, actually, the Hayabusa 2 and Osiris-Rex, that have actually landed on these asteroids, and also taken samples of them that can be studied in laboratory on Earth. And also the meteorites, of course, tell us something They are messages really about the early solar system, the inner part. Okay, so let's start our journey at the beginning. Let's start at the regions between the stars, these so-called interstellar clouds. So the space between the stars is not empty, but it's actually filled with a very, very, very dilute gas. And the denser concentrations of this gas are actually called clouds. And its stars and planets are actually formed inside these clouds. So let's take an example. Normally, I would now ask the audience to shout to me which constellation we are seeing here. So I'll listen for a little while and then can hear that most of you are probably saying that this is Orion, correct? And what you see here is the sword of Orion. And in the sword of Orion, we actually have the Orion Nebula. And what you see here in a blow-up and a beautiful image from the Hubble Space Telescope. That is actually the nursery of thousands of young stars that have just been born, just meaning only about 1 million years ago. Now, what you're seeing here is actually the red glow of the nebula. That is ionized gas. That is the recombination line of atomic hydrogen, the Balmer line that you're seeing here largely. That's hot gas. That's not where we find the molecules. We find the molecules actually in these dark regions that you see over here. These are the denser concentrations where the UV radiation can no longer penetrate. And that's where molecules survive. And that's also where stars and planets are being formed. So let's focus in on some of these dark clouds. So now we go to a different region. We go to the Carina Nebula, again, data from the Hubble Space Telescopes. And you see here these dark clouds now against a bright background nebula, a reflection nebula. And we can just here look at these clouds. And if I would point my telescopes at one of these denser parts that you see over here, and that's where I would find the molecules, and that's where I would find new stars being formed. So these clouds are actually so dark because they contain tiny little dust grains that actually absorb and scatter the visible light. And these clouds are also some of the largest objects that we have in our galaxy. They can have diameters of several light years, and they can have masses up to, say, 10,000 or maybe even 100,000 masses. So it can, in principle, form a lot of new suns. It will not do it. It will do it only with an efficiency of only a few percent, but still there's a large reservoir there of material in order to form new stars. So let's zoom in a little bit more on one of these dark clouds, which you see here as a silhouette against the thousands of background stars in the galaxies. These clouds consist primarily of hydrogen, and that's the most abundant element in the universe. Sort of 99% of it is gas, and that gas is mostly hydrogen. By mass, 1% is in these tiny little dust particles, and they are about a tenth of a micrometer in size. So if I take sort of one of my hairs, that's about maybe a millimeter in size, so still more than 1,000 times smaller than the width of my hair. And these tiny little dust grains, they are, it says dust, mostly silicates actually, like sand grains on the beach, and also carbonaceous material, so a lot of carbon in there. Temperatures in these clouds are very cold, only just above the absolute zero, and the densities are also incredibly low, about 10,000 particles per cubic centimeter, which is 1 million times less than the best ultra-high vacuum that you have in a laboratory on Earth. So here in your room or wherever you are in your house, 1 cubic centimeter contains about 3 times 10 to the 19 particles per cubic centimeter. And this good vacuum in a laboratory still has about, say, 100 million particles per cubic centimeter. So it's really very empty. And it also means that when an astronomer talks about a dark cloud, a dense cloud, it's actually still very, very empty. But nevertheless, atoms and molecules can meet each other. We have a lot of material and we also have long time scales. And that means that things can still happen. But nevertheless, these clouds are, for me, who originally was trained as a chemist, is actually a very unique physical chemical laboratory. Now, if we look at these clouds in the optical and the visible lights, then we see that these dark clouds there. That's nice. We know that there's a cloud there, but we don't learn much from that. We cannot see through it. We cannot see what is inside that cloud. In order to look inside that cloud, we have to put on different glasses, say infrared, go to the infrared or even longer wavelengths. And then you see that you can actually penetrate here into these clouds and see through them. So that means that we need to build also special telescopes for that actually can look in these wavelengths. Now, a large fraction of the infrared sky is actually blocked by our own atmosphere, all the water, all the CO2, oxygen, etc., that there is in our atmosphere actually blocks the signals from outer space in penetrating onto Earth. So you have to build satellites that can actually go above the Earth's atmosphere in order to study these molecules and also to get the bulk of the infrared radiation. And I've been fortunate to be part of several of these important new facilities from the 1990s to the Spitzer Space Telescope from the NASA in the 2000 era, and then most recently the Herschel Space Observatory, which is actually was the largest astronomical telescope in space, with a diameter of 3.5 meters, even larger than the Hubble Space Telescope. And just to show you progress of technology, this is an infrared map as it was in the 1970s and 80s, when you just had a single pixel receiver and were struggling to get a signal. And these are some of the beautiful images of these clouds that Herschel has returned to us. What we're looking at here is really the radiation, the thermal radiation from the cold, say 20 Kelvin dust. And what we see here also is the individual dots that we see over here, and that are point sources that are actually young star objects, stars that are forming at this moment here inside these clouds. We also have some telescopes on the ground, optical, and they also look in tiny windows in the infrared through the atmosphere. Most notably here, the very large telescopes of the European Southern Observatory, for example, the Keck telescopes in the US, and then the future, as was mentioned already, the extremely large telescope, the TMT, in which India is also involved, that are now starting to be built. If we go to longer wavelengths, then we get into the radio regime. And again, India has a very powerful giant meter wave radio telescope near Pune that you see here in this beautiful picture. And now we no longer have a single telescope, but we actually have multiple telescopes in an array of which we can combine the signals as in an interferometer in order to make a sharper images than we can have from any single telescope. And this is exactly the technique that we're using, not at radio, at centimeter wavelengths or meter wavelengths, but at millimeter wavelengths through the facility that I will be mostly talking about, which is the Atacama Large Millimeter Array, also called ALMA. ALMA is the first worldwide collaboration in astronomy. It's basically the Europeans through ESO, the North Americans, and East Asia actually coming together and building this wonderful array of some 66 telescopes on this high altitude plain in northern Chile. Now, why go to millimeter wavelengths? Because that is the wavelengths where we can observe the cold dust in the continuum. And this is also the wavelength range where most of the molecules have their primary rotational transitions. So when a molecule tumbles end over end in space, that is when it emits radiation through their pure rotational lines at millimeter wavelengths. And so ALMA was a fantastic project, also quite challenging project, a testimony to high-tech technology. Here you see actually the components coming from all different parts of the world coming together here in northern Chile. Here at sort of the mid-altitude facility at about 3,000 meters altitude, where the components were basically integrated and tested. And when they were tested, they were driven on a big, gigantic truck up the mountain to 5,000 meters. And then they were actually put into the array. And so the inauguration was about 7 years ago. But you see here on this plane, and I can assure you that every time that I go there, and I was there last about a year ago, it was again a breathtaking experience, both literally and figuratively, in order to be there on this high altitude plane. Good, so that is actually how we observe molecules, how we observe star and planet forming regions. Let me now say a few minutes something about the chemistry. So let's switch to chemistry. And I'm sure you've all had the periodic table in high school, but I'm not sure that you realize that the astronomers view the periodic table with a slightly different eye. For them, hydrogen is by far the most important, a little bit of helium, and these were both made already during the Big Bang, about helium about 10% in number. But the chemically more relevant elements like carbon, nitrogen, and oxygen, the elements out of which we are built, that are in our body, they are present only at the level of less than a promille, at the level of, say, a few times 10 to the -4 with respect to hydrogen. And these elements were made through nuclear fusion in the interiors of stars. And if you go to further down in the periodic table, you go down again by at least an order of magnitude in terms of abundances. So very cold, very empty, mostly hydrogen. Molecules, atoms maybe encountering each other only once every 10,000 years or so. So chemists had told astronomers, well, don't even bother. In looking for molecules, you won't find them. Unfortunately, the astronomers didn't listen. They had their receivers. They started tuning their receivers. And quickly, starting from the late 1960s and 1970s, they discovered one molecule after another. And here you see some examples. In these days, you can get, if you just point your telescope, say at Orion, in 10 seconds of integration times, you get this whole forest of lines. And that is chock full of lines of both simple and somewhat more complex molecules. Methanol that you see over here is a common one, dimethyl ether that you see over here, SO2, etc., etc. Now, each molecule has, thanks to the laws of quantum mechanics, their own unique fingerprint or barcode, and that's how we can uniquely identify them, both in space and on the ground. And just to show you the progress that we have now made with ALMA, so previously we're looking at sort of chemistry on the scales of entire clouds, but now with ALMA, it allows us actually to look much sharper. And we can now zoom into regions where stars and planets are being formed on the scales of our own solar system. So our own solar system is about 100 astronomical units, of say 50 astronomical units radius, and 1 astronomical unit is the distance from the Earth to the Sun. Good. So what you see here is now ALMA zooming in here onto this region. This is actually a disk-like structure here around this young star. And just again, in a few minutes of ALMA, you see here wells of lines, more than 10,000 lines, just in this little tiny part of the spectrum. And we actually have an image actually also in each of these lines. So just to give you again an impression of some of the molecules that we have found in this case. So we're now really looking in some of these complex molecules on scales of our own solar system. So say the orbit of Neptune or the orbit of Uranus. And that is where we find these relatively complex molecules already. With 2 carbon atoms, 3 carbon atoms. This is one of the new ones that we just found, propenal, and not yet propanol. But you see already that we're growing in complexity. Also some interesting molecules which have an CNO bonds that you see over here indicated, which are so-called prebiotic molecules, meaning that they have the potential of leading to molecules that could be become part of the origins of life elsewhere. So just to show you some of these molecular bricks for life, we've already talked about some of them. Here's this one of the simplest, sugar, although not yet a sugar in the chemical sense, glycoaldehydes. Here's actually ethanol, alcohol. There's quite a bit of alcohol in space. Certainly the Orion Nebula may have enough alcohol to fill some 10 to the 27 bottles of whiskey. But if you start to now look at some of the molecules that have not yet been detected, which may be just as interesting as the ones that have been detected, then we see here, for example, the simplest amino acid, glycine. Not that much more complex than some of the other ones, not yet been convincingly detected. Purine, pyrimidine, the bases that are part of DNA, also not yet found. And neither has this little molecule, caffeine, which is not important for the origin of life, but may be important in the maintenance of life, that has also not yet been detected. Although, as we will see, aromatic molecules are now being discovered. So this is actually one of the big questions that we have, is how far does the chemical complexity actually go? And just to show you again, one relatively recent highlight, and the first chiral molecule, here propylene oxide, has been detected, a molecule that has handedness. Although we don't know yet whether the left or right-handed side is more or less abundant, that we cannot determine yet, but at least some of these chiral molecules are present. Nitrogen-containing aromatics, here benzonitrile has been discovered a few years ago, and now there is a whole set of these aromatic molecules that are being identified as we speak, actually, by radio observations. There's also a whole class of molecules that we know are present as a class, but we don't know the individual molecules. And these are the so-called polycyclic aromatic hydrocarbons. So we don't know whether choranine is there or some other form of PAHs, but we do know that they are there as a class because we should see their infrared spectral signatures. And then the fullerenes, C60, C70, they actually have been detected in space. They were first discovered on Earth, and actually one of the Nobel Prize winners, Harry Kroto, he used to be an astrochemist, and he was actually inspired by astrochemistry to start looking for these molecules in the laboratory, and that's what led him to the discovery of Buckminster fullerene. So far, we've talked about molecules in the gas, but these clouds are cold, and these dust particles are also very cold, only 10 degrees, just barely above absolute zero. And so that means actually that these dust grains actually act as a deep freeze. In which molecules from the gas and atoms from the gas can actually freeze out onto the dust grains and then be hydrogenated. So, for example, and this is a very important one, oxygen can land on a grain and then be turned into water, carbon into methane, nitrogen into ammonia, and carbon monoxide, one of the more abundant molecules, will be turned into methanol. So we can see actually that the alcohol in space is actually literally here on the rocks. And it is these kinds of processes that we're actually simulating in our laboratory in Leiden. That is now under the direction of Harold Linnaerts, and where we're basically studying these processes at very low temperatures, the formation of these ices, the chemistry of these ices, the spectroscopy of these ices. Of course, we have to speed up timescales. We cannot wait for 10,000 years, but we can study the chemistry. And so through these combined experiments and theory, actually, we've learned that this is the main way in which we can actually form water on these dust grains. So maybe once a day, a hydrogen atom lands on a grain, it finds another hydrogen, goes off, makes molecular hydrogen, but it can also encounter an oxygen and make water. It can make molecular oxygen, and it can make, there we make hydrogen peroxide, and now we're gonna speed forward. There, now we've made 2 hydrogens, and now we speed forward, and now we see that we actually make a water layer on this grain. And so this is the way in which actually most of the water that is now on Earth, that is in our body, that was made actually in these cold clouds prior to collapse in forming our solar system. So as one of my colleagues put it, water on Earth is actually older than the sun itself. And this is actually something that we can quantify again through our observations. This is just an example of one of the beautiful Herschel spectra in detecting actually the water in such a planet-forming disk and quantifying that to show that there is enough water, about 6,000 oceans of ice present in this disk in order to form new planets. And this work has not gone unnoticed. Even the Big Bang Theory here put this on their blackboard. So the intermediate summary, before I go spend still a few more minutes on the planet, star and planet formation, is that interstellar clouds have a rich chemical composition in spite of the very cold and tenuous conditions, and that complex molecules and water are found around nearly all forming stars throughout the entire Milky Way. So building blocks for prebiotic material are widespread. Okay, a few minutes then on how a new star and planetary systems are formed, because such a cloud as we see over there will not be stable forever. It will eventually start to collapse under its own weight. And when it does so, it will form a protostar in the center. But because it has a tiny little bit of rotation, angular momentum conservation, it will form an accretion disk around the young star. And we can see that actually. So here is actually an animation of the Orion Nebula from the Hubble data, making a 2-dimensional image from Hubble actually into a 3-dimensional movie. And what we see here is all of these. Over here, we see here actually the protostars. And now we go into an animation. And what we see here is actually this envelope of this collapsing cloud. And when that is blown away, also by the radiation and by the jets that comes out of it, we see here this rotating disk here around the young star. And that is where new planets are formed. So that's nice, but unfortunately, these disks are incredibly small. So far we've looked on scales, say, of cloud, but the disks are really tiny, tiny, tiny there. And this is exactly why ALMA needed to be built in order to zoom in on these forming stars and disks. And ALMA is incredibly sensitive. You can just point ALMA for 1 minute at a young star and you can find its disk here. This is what we see over here. And we can then get statistics on how many of the young stars in a star-forming regions have these dust disks. In this case, about 70% of them are detected. We also see unexpected structures in these disks. So here is one of the first beautiful examples that ALMA gave here of a young disk in which you see these dust rings. And one of the possible explanations is that these dust rings are due to planets that are currently forming actually. Whoops. Okay, sorry, it looks like let's just stopped for a minute. Okay. Is that there is a planet there that actually seems to be excavating these regions. So we seem to be getting in sort of a new era of observational planet formation, where we see these disks and we see their structures, and we see their structures really on scales of our own solar system. Fascinating structures. We don't know yet what they are due to. Some of them may be due to forming planets, others may have other explanations, but it's certainly a very exciting time. And this is just some of the latest data that have come out of ALMA, where you see these fascinating structures there in these planet-forming disks. So again, what we have learned from these data so far is that also the ingredients for planet formation are likely to be common, and that we are now seeing sort of planet formation in action from the structures in these disks. Let me go back then to exoplanetary systems and the diversity in planetary systems, and to my love for astronomy and art. This is an engraving already from 1798 that shows not only our own solar system, as it was known at the time, but also other solar systems. These other solar systems were already speculated to have either less planets, more planets, closer by, further in. And this is exactly, of course, what is found now with these exoplanet surveys. We find some that are bigger than the planets we have in our own solar system, and some that are in between what we know in our own solar system. How does this come? Well, the answer must lie in the past, basically when these planets were formed in their circumstellar disks. Water again plays an important role there, especially water ice is important to promote planet formation. And maybe it's no surprise that in our own solar system, the giant planets are just beyond the so-called snow lines that you see here so beautifully in nature. And so just beyond the snow line that you see over here, where you have icy planetesimals, icy building blocks actually, that can promote planet growth. And so this is the challenge that we're facing at the moment, is that, what you see here in this animation, is that we have here these disks, these rotating disks of gas and dust, and in which we have small particles that can collide with each other and that can grow to bigger and bigger and bigger particles. There we see them growing and forming. Sometimes they shatter and they go back to smaller particles, but they can also grow and then eventually become planetesimal. And so if you would look sort of at the steps in planet formation, how do you make a planet like our Earth? Well, you start off with these tiny particles, these dust grains. You make them bigger and bigger until you get sort of these planetesimals, comet size. Those are the building blocks when gravity starts to take over. We get to planetary embryos, maybe lunar or Mars size, and they again can interact through gravity and then build a planet like Earth. And so what do we now know about this process from our own solar system? So we can look at the comets there. We've had a beautiful comet actually this year, Neowise. I hope that several of you have actually seen that with the naked eye. But we also had this comet 67P, on which the Rosetta mission actually landed, and could also actually sniff the gases that were coming out of the comet. So this was actually an experiment that was on the orbiter around the comet. The Rosina experiment was a very sensitive mass spectrometer, which you could see actually as then having a very good nose, so to say, to sniff all the gases that were coming out of the comet. And now we can actually compare that with what we see in our planet-forming regions with ALMA. And there we see that actually many of the same gases that we saw there are also actually found in various species that are found both in the comets and that are present in our young disks. And actually also quantitatively, there appears to be a quite close correlation actually between them. So what are the next steps? Well, the next steps are clearly also the quest to look and characterize the atmospheres of more mature planets. Our group has been looking at the earliest stages of planet formation, but we now have this large sample of exoplanets, more mature exoplanets, and the next generation of telescopes will actually look at the signatures in their atmospheres. And what signatures should they be looking for? So let's look at our own solar system, Venus, Earth, and Mars. And then you see that CO2 is present in all three of them, but only in the Earth spectrum you would have uniquely water and ozone. So those are some of the so-called biomarkers that people will be looking at. There are other biomarkers. Certainly water by itself is not enough. You need to look at a whole sort of collective of biomarkers in order to detect whether or not there would be there would be life there. And so that is exactly the sort of one of the main science drivers for the next generation optical and near infrared telescopes, the extremely large telescopes like the ELT, like the TMT, that can hopefully answer the question, are we alone? Here, for example, like our nearest Proxima Centaurus, just a few light years away from us. Certainly there's a planet there. This is an artist impression of what a planet could look like, but now we want to sort of understand also what its atmosphere is. The first telescope that will take a look at that will be the James Webb Space Telescope, which is planned to be launched in late 2021. And then, as I said already, the extremely large telescopes, which are being built at this moment and will start to become available in the second half of this decade. I would like to end by coming back to the sky and coming back to the International Astronomical Union, of which I'm the president at the moment. We just celebrated our 100-year anniversary, and we did that through a large set of activities, more than 5,000 activities in more than 120 countries around the globe. And I can encourage you to go back to our website where we have a report, colorful report that shows that. One of the activities was Name Exoworld, in which every country around the globe could name one star and one planet. And actually India has the name of the star Bipa and planet Santa Massa. So I think that it means a beam of light and cloud, cloudy atmosphere of the planet. So that is the planet and its star actually that was named by your country in an open competition. Another activity that we had was celebrating 30-year anniversary of the pale blue dot, just before the lockdown, celebrating this beautiful image from the Voyager 1 mission that looked back at Earth from beyond Saturn, inspired by Carl Sagan, who then said, look at that dot. That's here, that's home, that's us. And that's, I think, one of the most important messages that we can give as astronomy, is that we provide this perspective, also a little bit of modesty. We're that tiny speck there in the universe, and then also tolerance, because we are, after all, citizens of the same beautiful sky. Thank you very much.
Thank you. Thank you very much, Ryan. And so enlightening to us that we are also contributing to the International Astronomical Union. And I was not aware of this fact that you have recently completed the 100 years, and we are actually organizing this program. We should have been there last year itself, organizing such activities.
Yeah,
So nice.
India has been very active in these celebrations, so we really appreciated all the work that that India has been doing there, and they have a fantastic outreach coordinators program and everything. So
Sure. And I think
really,
your
it's
talk
really a
will.
pleasure to work here.
I think your talk will definitely motivate a lot many young men, women, students to take up astrophysics as one of the career options later on. Thank you very much, Professor Yan. And on behalf of the NASI Delhi chapter and the host institution, the Upadhyaya College, I would like to thank you for giving this special public lecture and enlightening all of us about the various topics and the research which is going on in the areas of the black holes and all of the things.